Hello everyone, and we want to continue on the topic of relative permeability. And in this topic we define the relative permeability to be, for example, for the oil phase to be the ratio of the effective permeability of the oil divided by the absolute permeability, and so on and so forth for water and gas. Now in the Darcy's equation, when you want to use the when you have a multiphase flow, as you remember, this was the Darcy's equation, and if you want to calculate the flow rate of one phase, such as oil, in that equation you have to use the effective permeability of the oil, not the absolute permeability in the multiphase systems. Okay, and you have to use the pressure drop across the oil phase. You have to use the viscosity of the oil. Now, based on this equation, the relative permeability equation, KO is equal to KRO multiplied by absolute permeability, right? So you can substitute, instead of KO, you can substitute the equation for the equation which involves the relative permeability, and that equation becomes KRO K absolute A delta PO over mu OL. Now in reservoir simulation, it's easier to, if you do some experimental measurements, for example, you have a core sample from a reservoir, you do the relative permeability experiments, and I'll show you that how relative permeability is a function of saturation. And in that case, if you have a reservoir and then you want to simulate that reservoir, you want to simulate the fluid flow inside that reservoir, you can basically find the relative permeability at each location inside the reservoir based on whatever saturation of each phase you have inside that location. So this one will come from the experiment, absolute permeability. This will come also from the experimental measurements of relative permeability for each location inside the reservoir. Then you can use this equation instead of that for your reservoir simulation. All right, so same for water, same for gas. You use basically the same substitution because the equation for relative permeability is similar to each other. And we actually defined this. We talked about the absolute permeability. Again, I'm going to remind you that the absolute permeability is measured when you saturate your core sample 100% with brine or water and then measure the permeability. We do have the air permeability. Remember, we did the gas permeability using the Klinkenberg effect, and if you calculate or measure the air permeability at different mean pressures between the lower and upper point of your sample, you can use that to calculate the absolute permeability using the Klinkenberg effect, right? Anyway, so now I just mentioned that the relative permeability is a function of saturation. So basically, if you have a pore that you have more water inside that pore, then experiments have shown that the relative permeability of the water, for example, if you have more water inside that pore, would be higher compared to the case that you have less water. So considering two pores, let's say this is one pore, pore number 1, and pore number 2, and then you have, let's say, this much of water inside this pore and this much of oil, and in pore number 2 you have this much of water and then the rest is oil. Experiments have shown that the water relative permeability in pore number 1 is higher than the relative permeability of water in pore number 2. So relative permeability is a function of saturation. Now you can say that in a two-phase system of oil and water, relative permeability of water is a function of water saturation, or basically relative permeability of water is a function of 1 minus SO, right? Or relative permeability of water is a function of just oil saturation, because water saturation is equal to 1 minus oil saturation in the two-phase system. Now in the three-phase system, however, you have 3 different saturations, out of which 2 are independent. So for example, in this case, we are reporting the relative permeabilities as a function of oil saturation and water saturation. The first one is oil, which is 0.5. The second one is water saturation. So you just need to mention two of these saturations because the other one is just 1 minus 0.5 minus 0.3. Now, that's true for oil relative permeability. This should be G, which is not correct. And this should be G as well. Okay. So, that's the definition, right? So this is a function of water saturation, right? The relative permeabilities, and apparently all these are not correct. They should be, this should be W. That's O, right? Anyway, so we have this relative permeability as a function of saturation, but how does the function look like? So on this figure, you can see on the right side that there are two curves. First, the y-axis is your relative permeability, which we mentioned that it's a number between 0 and 1. 1 suggests that your effective permeability of that phase, for example, if your relative permeability of water is equal to 1, that means that effective permeability of water is equal to absolute permeability, which is the case for single phase flow systems, right? So at KRW equal to 1 or KRO equal to 1, you are dealing with a one phase system. Okay. Anyway, so again, I just should mention that one phase system does not mean that you only have one phase in your system. One phase system means that one of the phases only move. Okay, so you might have a system at which you have 20% of irreducible water saturation, and that 20% doesn't move, right? And you have 80% of oil saturation, but that system is a single phase system in terms of fluid flow in porous media, because you have basically only oil moving. Alright, so looking into these curves, you see that there is an oil relative permeability curve, which is shown with a green line, and you see a water relative permeability curve. The y-axis is relative permeability, fraction between 0 and 1. The x-axis is water saturation, so this is a two-phase system only, and we are drawing relative permeability as a function of water saturation, which is between 0 and 1. Okay, so let's look at the numbers, how they look like. So first you see that there are a term which is called imbibition, you see on the top of this curve, right? So remember, we defined the imbibition to be a process in which that the saturation of wetting phase increases as the process going on. So saturation of wetting phase increases inside your core sample or your reservoir or your porous media. Wetting phase increases, and drainage was a process where the saturation of wetting phase decreases as the process is going continues, right? So now look at this. How do we understand that if this process is imbibition or drainage? So there is a arrow showing the direction of the process. So the way you should think of this curve is such that you initially had a core sample at this point. Okay, so a core sample at which the water saturation was 20%. So state 1 or time 1, your core sample, you have 20% water saturation, 80% oil saturation. Now that 20% water saturation is, if you look at the relative permeability of water at 20%, what number do you see? 0, right? What does 0 means for relative permeability? Look at the Darcy's equation. If you put 0 for relative permeability, it means that Q is 0, which means you don't have any flow, right? So when you are at 20%, you don't have any flow, which means that 20% is irreducible water saturation. Okay, so SW irreducible is 20% for this specific process, right? Because relative permeability of water is 0, and at the same saturation, the relative permeability of water oil, which is the green curve, is 1, right? So oil basically is the only phase which is flowing inside that porous media. Now the process continues in this direction, which means that you're going down, right? Let's say state 2 is here, right? And at state 2, we have around 50%, so you have your core sample again. Now what are you doing here is you inject water into the core sample because this is an imbibition process. Okay, so let's say you are here, right? You start injecting water into this core sample. So the saturation of the water starts to increase, right? You see the direction. The saturation of the water is increasing from this point to this point, right? From 20% maybe to 30%. So SW becomes 30% at point 2. You are injecting water. You displace the oil with water, right? So the oil saturation, therefore, is 1 minus that, or 100% minus that, which is 70%, right? Now, at state 1, the relative permeability of oil was equal to 1, relative permeability of water was equal to 0. At this point, relative permeability of oil drops to 0.5, right? I'm just reading that point from the relative permeability curve. So KRO is 0.5, and KRW, at that point, you have to use the blue curve at that specific saturation. So it's around here. So very, very small still, right? I don't know, it might be around 2 or 3%. So I'm just gonna put 0.04, maybe 4%. Okay. One thing that about the relative permeability is that it's not like saturation that the summation of these two should be equal to 1, right? They could be different numbers, but they should be between 0 and 1. Here it becomes 1, but it doesn't mean that it should be 1 for all the saturations. Okay, so that there is not such a relationship that the sum of the relative permeabilities should be 1. Okay. All right, so so we have this so far, right? And then we go to a point at which these two intersects. That's at for this specific case is 60%. Okay, and in this at water saturation 60%, the relative permeability of the water and oil becomes the same. And finally, we come to a point. We'll talk about this point later on. But finally, we come to a point at which the water saturation becomes 80% and the relative permeability of the water becomes around 18%. And what happens to the relative permeability of the oil? Let's say this is 0.3, right? At 0.3, the relative permeability of oil becomes 0. The relative permeability of water becomes around maybe 80%, 18%, or 15%, I don't know. And now you have a core sample which is 80%, which has 80% water and 20% oil. Now you have still oil inside your system at this point, but the relative permeability of oil is 0. What does that mean? You have a residual oil saturation, as we call it, of 20%. It means that 20% of the oil is immovable inside your porous media and you cannot move that. Okay. And that's it, right? So that's called SOR. This is called SWI, and SOR is 20%. Well, actually, it's not exactly 80%. It's 70 something percent, right? At this point, so the correct number may be 75%. So 75% and 25% here. So that should be 25. Okay. Anyway, so we'll continue on this topic on the next video.